Okay, so we have a police car sounding a siren with a frequency 1580 hertz, and the speed of the police car is 120 kilometers per hour. Now we have to find out if we have a stationary observer standing next to a road. We have to find out when the car approaches or recedes, what frequency does the observer experience. So in other way, how the frequency changes if the car is approaching towards him or receding from him. So first of all, let's see what's given here. We have the frequency, which is 1580 hertz. We have the velocity of the source, or in our case, it's the police car with the siren. So it's 120 kilometers per hour. And then this velocity of the sound is given, or we get that from our textbook, uh, which is 343 meters per second. Now, you see, the units are not consistent, so we have to make the units consistent here. So we can change our kilometers per hours to meters per seconds to be consistent. So let's do that. And to do so, what we're going to do is um, we try to get rid of our kilometers per hour unit. So if we multiply 1 meter per second on top and put 3.6 kilometers per hour at the bottom. So this is basically same as 1 meter per second, because um, an hour is equal to 3600 seconds. So that's why you have 3.6 kilometers per hour, which is, when you divide these guys, you get rid of the number and it becomes 1. But anyway, so if we do this, we get rid of this kilometers per hour unit, and we end up having this as our velocity of the source. So we need this for the rest of our calculation, so we need to remember this number. So we have 33.33 meters per second as our velocity of the source, and then the velocity of the sound is 343. Okay, so let's see what we need to do. So if we look at equation 12.2 and 12.2b, these two equations kind of explains what happens if if the observer is stationary and then the source is moving towards you or moving away from you. So if it's moving forward, then you have this equation, and if it's moving away, we have this equation. So one important thing to remember here, or about one note about the sign, is if the source is moving towards us or towards the observer, that means your frequency will be increasing. So whatever frequency you have when both of the objects are stationary, it will start increasing if the source and the observer start to come towards each other. And similarly, if the source is moving away from the observer, then you will have your frequency will be smaller. So we can so if we don't understand how to put the sign, there's one way to um, remember how to mathematically put the sign. So you see, if we are subtracting this quantity from 1, that means this guy is lesser than 1, so this quantity is basically bigger than whatever f you have. So and yeah, so if we put all the numbers here and do the calculation, we actually see that's happening. So we get 1750 hertz, which is greater than 1580. And so when it's moving away, we are adding this number, so the denominator becomes greater than 1, so that makes this guy, that makes that guy less than 1. So if we multiply f with a number lesser than 1, we get uh, the lower frequency, and that's one way to verify. Okay, for part B, yeah, for part B, both source and the observer are moving, but they are moving in the opposite direction. So they're moving. Let's see. Okay, so yeah, so they're moving in the, I don't know what's happening. Anyways, so yeah, they're moving in the opposite direction, and if we again look at the equation, if we again look at equation 12.4, we get an expression for this type of calculation. Now we are given the velocity of the observer as 90 kilometers per hour. Now we need to change it to meters per second, and we do the same trick that we did before, and we get 25 meters per second as our velocity. Now rest of the information is known. So the equation becomes velocity frequency approaching equals frequency times velocity of the sound wave plus velocity of the observer, velocity of the sound wave minus velocity of the source. Now again we have to apply the same trick because it's approaching. That means our final frequency should be higher than the fundamental frequency that we had, and to do so we have to make the numerator bigger than the denominator. So um, that's why we're putting a positive sign on top and putting a negative sign at the bottom. And if we do the calculation, we see we get 1880 hertz, which is greater than 1580. And for receding, we put a minus sign on top and put a plus sign at the bottom, and that gives us a number which is smaller than 1580, because this guy is now smaller than this guy, and then you get a number less than 1, and that's why you're getting a smaller number. But yeah, that's how you do part B. So for part C, yeah, for part C, the police car and the other car are traveling on the opposite direction. So that means sorry, at the same direction. So that means the only thing that will change is the sign at the top. Because if we look at this equation, we have this positive sign and negative sign at the bottom, and then we have negative sign here and positive at the bottom. And again, we're using the same equation 12.4. So if we look at the equation carefully, the one that calculates the approaching has a negative sign here and a positive sign and a negative sign here as well, right? So the only difference between this equation and the previous equation here is the sign on the top. And similarly, for the second equation, when the car is receding, you have a positive sign here and we have a negative sign here, but the sign at the denominator, it remains unchanged. And again, if we carry out the same expression, now we have 80 kilometers per hour as our observed velocity, or the observer's velocity. So we do the same trick, get 22.22 meters per second as our velocity, and we put all the numbers, and we see that the approaching is again bigger than the initial frequency, and receding is smaller than the smaller frequency. Okay, thank you.